So covalent compounds, remind me, how do they bond together? By, you said what? Sharing electrons. Please hear me, friends. The charges do not matter. Okay? There's a number of you on your test, even on the retakes, you were still talking about the charges when fluorine and oxygen were coming together. The charges don't matter. Because fluorine and oxygen are both negative. How could they come together, right? They can't, ionically. They can covalently. If they share the electrons, because then their job is just to try to get to 8. The magic number, right? That octet rule. Does that make sense? So that's what this lab is all about, covalent compounds and how we put them together and how they bond together. Okay? But that's our key, is this magic number 8, the octet rule. Okay? So the first thing that your lab taught you about was about these Lewis electron dot diagrams, right? Has anybody heard of these before? Had you heard of them before we did this? Okay, a few of you. Yeah. What do the Lewis electron dot diagrams, I call them Lewis dot diagrams, that's what I learned them as. What do Lewis dot diagrams tell us? Like, what's the point behind them? Sir? How many electrons total? Valence is what Nathan said, and I agree with that. Because remember, the valence electrons, and we're going to say this like 1,000 times, Marlon, over and over and over again for the course of the year. Valence electrons are the key to how elements react. Okay? That is the key point. So, if we're looking at an element, and we want to know how it's going to react, if we look at its valence electrons, we'll get a clue. So here's my hydrogen. How many valence electrons does hydrogen have? Well, how many total electrons does hydrogen have? 1. That's it, right? It's got 1. Its atomic number is 1. It's got 1 proton and 1 electron. So therefore, we would simply put 1 dot for electron, for hydrogen. And there is no rule about where the dots go, by the way, or in what order they go. I usually teach you start on the right and go counterclockwise, but it doesn't matter. Okay, you'll see them a number of different ways. So this is the Lewis dot diagram for hydrogen, to tell me, hey, hydrogen only has 1 valence electron. Make sense? Okay, how about for boron? Sorry, let me switch colors. How about for boron? How many valence electrons does boron have? Boron's number 5, right? So 5 total, but how many valence? 3. It's in group 3, right? It's a main group element, so the group numbers tell you. So 3, 1, 2, 3. I'll make them bigger so you can see them better. Sir? Sure. So you wouldn't want to double up the dots until you've got 1 all the way around. Does that make sense? That is a pretty solid rule. We don't double them up until we've got 4 dots around there. How about for nitrogen? Nitrogen has 5 valence electrons, right? It's here in group 15. So therefore, 1, 2, 3, 4, 5. And again, the 2 can be on any side. Doesn't matter which way you do it. That was just the way I learned, so that's the way I teach it. Does this make sense? Fairly straightforward, right? And remember, it's not the number of electrons. It's the number of valence electrons. So you should never have more than 8 around for a Lewis dot structure. Does that make sense? You would never draw it with 15 or 20 or 82. No. Just valence electrons. Any questions here? So you did silicon, right? Si. I'm looking at pre-lab number 1, by the way, if you haven't noticed that. That's where I'm at. How about silicon? How many dots should be around silicon? 4, right? How about for sulfur? 6. How about for bromine? 7. How about for argon over there in group 18? There should be 8. Does that make sense? Okay. So based on those Lewis dot diagrams, now we can build what are called Lewis structures. And those structures are basically where we are showing how two elements are going to bond together to make a compound. Does that make sense? And we can do this for ionics, but we're focusing on covalence here. And what they do is when there is a bond being formed between two elements, we draw a line to show us that bond. So, let's take two fluorines. Well, so fluorine has how many valence electrons? It's in group 17, 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay? And then here is another fluorine. 1, 2, 3, 4, 5, 6, 7. We cool? How many more electrons does fluorine need to be happy? 1. It needs to get to 8, right? And it's got 7. So therefore, how many electrons should it share if I want to put two fluorines together? If each of them share 1, they'll be happy. Does that make sense? So what we're saying is that there's a bond that's being formed. Let me actually draw that in a different color. A bond being formed here. And this guy can go with here. So 1, 2, 3, 4, 5, 6, 7, 8. Right? And this guy can go with here. 1, 2, 3, 4, 5, 6, 7, 8. And everybody's happy. But again, notice, it's not that I came as one fluorine and took Carissa's other one so that now she's positive and I'm... Right? That would have been an ionic bond. What we're doing is we're basically saying, hey, can we both be happy, and if I share one and you share one, and we can both be cool. Does that make sense? Are we good? Sir? We're not dealing with charges at all. No, you're correct. Because again, I'm not actually stealing her electron, or she's not actually taking my electron. We're just sharing. We each want to get to 8, and I'm not strong enough to take hers away. She's not strong enough to take mine. So let's just share so we can both be happy. No, these are just elements all by themselves. No charges at all. The charges are only for ionic compounds. We only deal with this as being a -1. It's only when it takes on an extra electron to be happy. But that's an ionic bond, not covalent. Sir?
So, when cations and anions form, is it a natural process, or does it happen something?
They'll usually form in reactions. You're correct. But can you have electrons that are just added and taken away? Yes, you can do that as well. But normally in a reaction. So how would you draw a Lewis structure for this guy? Well, I have one F, I have another F, and I'm drawing a line between them. To simply say, hey, they're sharing one pair of electrons. Each line means one pair of electrons. Does that make sense? Sir? No. For a Lewis structure, you're just simply drawing the symbol with the lines. For a Lewis dot diagram, yes, you would do that. You see the difference? Much simpler, right? And the point of this is just that they'll tell you how many valence electrons we have. Sir? Sure. So if I had two oxygens that are together, right? Oxygens have how many valence electrons? They're in group 16, so they have 6. So how many more electrons do they need to be happy? 2. So how many electrons do you think they're going to share? 2. So therefore, you'll have 2 bonds being made, which we call a double bond, right? And now they're both happy. So if another element is added, if the oxygen is more attracted to that element, it would break this bond and react with them. And that's often what happens. This is not a super strong bond. Because oxygen reacts with almost anything. It's super reactive. So it would just break that bond and form another bond that's more stable, that's more attractive. Can I hold that one for 1 second? I have one more to do, and then we'll do that one, I promise. Okay? What if instead of doing oxygen, what if we had nitrogen? How many valence electrons does nitrogen have? It's got 5. It's in group 15. So how many does it need to be happy? 3 more, right? Because you're going to go to 8. So what do you think it's going to do? It's going to share 3. It's going to form a triple bond. Way back in the day, one of my students called this a James bond. Why, I don't know, but that's stuck with me ever since. William Arthur, do y'all know who William Arthur is? Anyway, shout out to William.
So is there a limit to how many bonds they can have? Whoever past 5 or like 8?
So normally 4 is about the most you're going to make. In your pre-lab, they talked about some exceptions to that, where sometimes you can make 5 or even 6. Like phosphorus tends to make 5. But those are exceptions. Usually 4 is about the most. And the key is they're going to make those bonds to fill up until they get 8. Like that's the whole point behind them making bonds, is to get to that magic number 8. Make sense?
What if it's 2 different ones?
Oh, we'll get to that one, yes. Let's talk about these now. So I'm going to go back to that water question, which is exactly where I was going to go next. So I'll have to slip you your $20 later, Marlon, for making that transition. I appreciate that. Okay? Because we're talking about shape. That's another thing that this lab is dealing with, is the shape of molecules. Are you comfortable that these guys are just going to be straight across from one another? Like in a line, which we would call a linear molecule? Does that make sense? But what if I were to take, so for example, if we have H2O, right? So 2 hydrogens and 1 oxygen, right? Well, the oxygen's there. And we're going to have 2 H's that are going to be bonded, right? Now here's our trouble. H's are the only element, well, okay, helium as well, but it never bonds, that only needs 2 valence electrons. Remember, everything else wants 8. Why does hydrogen only want 2? Right, because that 1s, yeah. Right, the 1s only holds 2. So once it gets those 2, it's happy, right? It's filled. Are we comfortable with that? So you might tend to say that these guys would be a nice linear shape as well, right? Just going like this. As a matter of fact, if I had carbon dioxide, which is a carbon with 2 oxygens, this would be a nice linear shape, right? But here's the trouble. Oxygen, we're only sharing 2, right? But how many valence electrons does oxygen have total? It's in group 16. So it has 6. So are you comfortable that there are still 2, we call them lone pairs, 2 pairs of electrons that are just hanging out together? We cool so far? And I guess your question, 1 second. We good so far? And the thing about it is, what charge do electrons have? They're all negative, right? If I take 2 negative things and put them together, what happens? Do they attract or repel? They repel, right? They want to be as far away from each other as possible. So therefore, instead of this staying a nice straight molecule, those lone pairs are going to push the 2 O's, excuse me, the 2 H's down. For carbon, we don't have that, right? All of its electrons are in bonds, so therefore it stays linear. This guy, if I want to make it like 3-dimensional, you've got a lone pair up here, a lone pair here, here's my O, and then my bonds with the H's. If I can use the models that you all are going to use in the second part of this, I forgot they're back here. Our water would look something like this. So these little Mickey Mouse ears, those are lone pairs. This would be the oxygen in the middle and the hydrogens on the end. You see how instead of it being straight, it's now bent those hydrogens down? Does that make sense in the three-dimensionalness? So we very creatively call this shape a bent shape. I'm not kidding, that's really the name of it, a bent. That's its molecular geometry is bent. Are you with me, my friends? Oh, sorry, you had a question first.
In this case, are we always going to show
The lone pairs up here? Yes. Right. So this is where, again, those Lewis dot diagrams and the Lewis structures kind of combine together, where you're showing the geometry because of those guys. Okay? Your question?
Go back to the nitrogen one.
I'm sorry?
The nitrogen
Yep.
Shouldn't we write two?
That's right. So you're right. Technically, there should be twos over here, and that's fine. We kind of ignore them because they don't play a role in the shape at all. So that's why we didn't write them. And frankly, these guys have got these guys over here as well.
So on our test, if we don't write it,
Right. As long as it's not affecting the shape, I wouldn't worry about it. Yeah. Are you with me, friends? Maybe, possibly, potentially. It's a lot more talking than I wanted to do today. Okay. In your pre-lab number 3, they talked about the exceptions to the rules. You gotta love exceptions. High school chemistry students hate exceptions. You all want rules. And I get it, that's cool. That's why we deal with more main group elements, because they follow the rules, but not always. Okay, so let's do one of these like what you're going to do in part A. Okay? So in part A, if you look at that table, you have a list of names of elements, right? Some of them are full compounds. Some of them are polyatomic ions. Some of them are names that you won't recognize, like methane or ethylene. You'll have to look them up. Okay, they're in your textbook, or you can use that Google thing. That's fine. Okay, to find the formula. And they walk you through how we make these Lewis structures. And I have to make sure you understand. There's like 1,000 rules you could set up to make these structures. We're doing the basic ones together, okay? So don't freak out. We'll just follow the rules, okay? So here's what it says. We're going to start off with this compound, COCl2. We good? This is just the example we're going to do together, okay? So it says, write the formula. Number 2, count the number of valence electrons supplied by each atom. Okay, how many valence electrons does carbon have? 4. That's 4. You mean you get a PT out. How about for oxygen? 6. How about for chlorine? 7 times 2, which is 14. Notice because I've got 2 chlorines, right? So how many total valence electrons do I have? I got 24. So 24 valence electrons is what I have to work with. Are we cool? If for some reason what they gave you was a polyatomic ion or an ion of some sort, if it had a positive here, right, then I would take away a number from there. If it had a negative, I would add that number to there. Because we're talking about number of electrons, right? Again, I'm reading right from here. It's in your instructions. I'm afraid I may have lost you already, because I've been talking for a while. Okay, so we go to the next step. That was step 2. Sir? Yes, you just add 2 or add 3. Exactly. Number 3, use the following guidelines to draw a Lewis structure. Okay? Keep in mind that there are some exceptions they talked about in the pre-lab. So we draw a skeleton for a molecule by joining atoms with single bonds. If we only have one element, then we use that as the center. But I've got carbon and oxygen that only have one of them. I'll give you a clue. If carbon's around, it's going to be in the middle. Almost always. So we'll put carbon in the middle. And then we'll put a single bond to chlorine and a single bond to chlorine and a single bond to oxygen. That doesn't really look like an oxygen bond, sorry. We cool there? So how many electrons have I used so far? Because each of these stands for 2. So therefore 3 times 2 would be 6. Good. So I take away 6 here, so I'm down to 18 left. Are you with me so far? Okay. How many electrons does each element need? 8. Remember, except hydrogen only needs 2. So, can we fill in the rest of these and see if we can't use up all 18? Can we do that? So chlorine has 2 here, so let's put 6 there. So now chlorine has 8. Are you with me? So let's take away 6. So now I got 12. Let's add 6 more over here. 3, 4, 5, 6. So minus 6 gives me 12. Oops. Sorry, Mr. S can't add today. My apologies. Minus 6 gives me 6 is what I meant to say. Okay. And then I've got 6 left. Where are those guys going to go? With the oxygen. Good, good. 1, 2, 3, 4, 5, 6. And now we've used them all, right? Are you with me so far? Okay. So, does chlorine have 8 atoms around it? It does. Does the right side chlorine have 8? By the way, don't forget that each of these is worth 2, right? Are you with me? Okay, so this has got 8, this has got 8, oxygen's got 8, but what doesn't have 8? Carbon. Carbon's only got 6, right? Are you with me? I'm going to have to share. You have an idea? Okay, question, please.
So if they're sharing 2, if carbon is sharing 2, then why are there 2 lines?
So each line stands for 2 electrons. Because it's a bond between 1 electron from carbon and 1 electron from chlorine. It's a good question. Sir? It would have to do a double bond with oxygen. Why not with these guys? Well, because they only need 1. Remember, chlorine has 7 valence electrons, so it only wants to share 1, and it's happy. But oxygen has 6, right? So it would be very comfortable sharing 2 with this chlorine. So it's going to take one of those pairs, and instead it's going to make a double bond here. Does that make sense? And now if we count them up, chlorine has 8.
Pardon the interruption. Teachers, if you could please check your email. I have something I need you to check right away, please. Thank you.
We're pausing. Okay. No worries for us. Everybody has 8. Are we comfortable there? Question.
So oxygen just gave, shared 2 of its electrons?
Yep. And remember that carbon has 4 valence electrons, right? So that makes sense. It's going to share all 4 of those, 1 with chlorine, 1 with chlorine, and 2 with oxygen. And in response, it gets the rest that it needs. So you could theoretically, but again, oxygen has 6 valence electrons, so it needs 2 more. It needs to share 2 to be happy. It had only shared 1 initially. Does that make sense? Question? Okay. Yes, sir. You would, yeah, because it would not want to do that. It would want to do it with oxygen. Yeah, definitely. Are you with me, my friends? So again, I'm just following along in part A of your lab. You see the procedure, right? Where I'm reading what I just read you, we literally go down through. Okay? And sometimes you'll have multiple ways. Like let's say that there would have been 1 chlorine and 2 oxygens, then you could have made the double bond with either oxygen. Does that make sense? So there will be multiple ways that you could do some of these. So don't freak out at, well, is it over here or is it over there? It could be either. Okay? Here's what I want you to try. And again, this took way longer than I expected. I want you to begin at least writing the formulas for all of the parts in Table A. You with me? There's Table A and there's Table B. So let's at least write the formulas and counting the valence electrons between now and when I see you again next. And we'll spend some more time working on the structures tomorrow. Actually, it's going to be Monday because there's nothing to do with you tomorrow. Does that make sense what I'm asking you to do? We do. I just have another activity we're going to do tomorrow.